Hi everyone, welcome to another LIC class. In the previous class, we started op-amp multivibrators. Op-amp multivibrators are the type of op-amps that generate pulsating signals. Usually they are used for clocks and digital systems, or they are used in applications called the pulse width modulation or PWM. It's an op-amp with a feedback with an RC oscillator connected to it. We spoke about how we determine the frequency and how an op-amp multivibrator functions. And we solved a couple of problems, practice problems as well. Today, we will start with op-amp competitors. And I would explain a little bit about op-amp competitors. What are the functions? You're already familiar with op-amp competitors. I've just added more explanation here. So what is an op-amp competitor? It's an electronic decision-making tool. It has two inputs and compares them. And if the positive input is greater than the negative input, you would have a positive voltage in the output, which is usually the supply voltage, supply rate voltage. And if the negative voltage is greater than the positive voltage, you're going to have a negative voltage in the output. Since an op-amp for an ideal, the gain for an ideal op-amp is infinite, therefore V out is going to be A, V positive minus V negative. And if what V positive is greater than V negative, then V out would be equal to positive VCC if V positive is greater than V negative. And if V positive is less than V negative, then V out would be equal to negative VCC. As mentioned, there is a transition slope between when the output is changing the status from a negative to a positive or a positive to a negative, depending on the slew rate, how fast this is. It could be a couple microseconds up to a few milliseconds. And this is just the explanation that we already gave for op-amp competitors, nothing new here. The thing that I want to focus on today is the competitor reference voltage. Sometimes we can connect one of the inputs of a competitor to a reference voltage. And using this reference voltage, we can determine the output of the voltage and actually adjust the output of the voltage. These are 4 different types of competitor reference voltages. The first one is connected to the V negative or V reference here is connected to two resistors, between 2 resistors, and it's forming the voltage of the reference is determined by the voltage divider equation, and V reference would be R2 over R1 plus R2 VCC. In this case, V reference is fixed. So for example, if we fix it at 1 volt, you can't change it. A more advanced version is, instead of using 2 resistors, is to use a potentiometer. If we use a pot or a potentiometer, we can adjust the reference voltage, therefore, and we can change it. So the one on the left, again, it's a fixed voltage divider reference source. The one on the right, the upper one, is a variable position reference source. Third one is just to use a DC battery reference voltage. So instead of just having resistors and a power supply, we can just use the DC path, and the power supply could be directly connected to the reference source. And the fourth one, so for the third one, V reference is equal to the battery voltage. And for the fourth one, we connect the reference voltage to a Zener diode. And as we know, Zener diode actually works as a voltage regulator, gives you a fixed voltage. Here again, V reference is a fixed voltage, which is equal to VZ. So number 1, 3, and 4 have fixed voltages, and number 2 has a variable position reference source. Now, what are the applications for these? Imagine you want to turn on a light with a sensor, and that sensor is a light sensor. Imagine you have a dusk to dawn light, and you want it to automatically turn on when it's dark, and you want it to turn off to preserve energy when it's bright outside, it's daylight. So during the day, you want to turn it off. During the night, you want to turn it on. What I can do, I can connect this VN to what we call a photoresistor. A photoresistor is a type of resistor which its resistance changes with light. If you usually have a brighter situation, you have a lower resistance, darker situation, you have lower resistance. And then I want to connect this to a battery. Let's say this is a 3-volt battery. During the day, the voltage, let's say the voltage goes to 2.5 volts. And during the night, I'm going to draw it with black. It goes down to 1.5 volts. I want to set this reference voltage. So whenever the voltage is less than 1.5 volts, the output would be equal to V negative VCC. So what I can do here, I can set the reference voltage to 1.5 volts. So anything greater than 1.5 volts is going to be negative VCC. Anything less than 1.5 volts for here, it's going to be positive VCC. So I can set this reference voltage and adjust R1 and R2 in, so that the output voltage will turn on or off a light. So I'm going to show the light bulb with this. Let's just show it with L. I'm going to show it with load L, which is a light bulb. Could be a light bulb, it could be a motor, it could be anything. But there is a problem with this. Can you tell me can you think of a problem on this one? So it works pretty good in most situations, but it has a big downfall. So the downfall for this one is you don't have any control on you don't have a lot of control on when you can turn on and off the light. Do you want it to be completely dark to turn on the light, or you want it to, like when it's in the evening, you want to turn on the light? Since you don't have any control on the reference voltage, you cannot, once you fix it, you can't adjust that. So that's the problem with the first one. You don't have a lot of control on when you want to turn on the light or when you want. And once it's fixed, you can't change it. Second one solves this problem. And most of these dusk till dawn lights, you would see that some of them have this small potentiometer knob that you can change, and you can adjust when do you want to actually turn on and off the light. You can go all over to the extreme and keep it completely on. You can take it completely off. When it's completely off, for example, V reference would be 0 volts. V positive or VN would never reach 0 volts. Therefore, it's going to be completely turned off, for example. And you can put VRF as VCC, and it's going to be completely turned on, for example. So You can have control on when you want to turn it on, how sensitive you want that photoresistor to be. Do you want it to be turned on when it's completely dark, or even if in the evening or in the dawn when you have a little bit of light, you want it to be turned on? So that second one we have control of it. But the second one has still second one has a problem that the third one has as well. So instead of having a potentiometer and a voltage source, we can just get rid of this potentiometer and directly connect this to a voltage source, which here is a battery. It makes it simpler, but again, in case number 3, you don't have any control, because once you set that and connect it to the battery, you have set the reference voltage and you can't change it. So I would say 1 and 3 are very similar to each other. The only difference between 1 and 3, in 3, you have directly connected that to the op amp. The benefit that 1 has compared to 3 is that sometimes you can't connect an op amp directly to a battery, especially if you have a large battery. These op amps have limitations of how much voltage you can apply to this input voltage. If it's a large voltage, it's going to damage the op amp. So number 1 has a protection compared to number 3, but they both have the same problem. They are fixed. Once you fix the reference voltage, you cannot change this reference voltage. But number 1, 2, and 3 have another problem that is solved in number 4. Can you think of a problem that these systems have? Again, for those who just joined the class, today we're speaking about voltage comparators. One, as you know, voltage comparator compares the input voltages. If, for example, the input positive voltage is greater than the negative voltage, then the output voltage would be positive VCC, and the opposite. Actually, we have the table here. And if the input, or V negative, is less than V reference, you're going to have negative VCC. How can we use it? One application for this is, for example, if I connect this to a photoresistor, if I connect Vn to a photoresistor, I'm able to turn on and off a light and create like a dusk to dawn automatic light system. This is 4 different configurations of a comparator reference voltage system. The first one simply uses a voltage divider. The second one is using a variable resistor or potentiometer connected to the V reference. It's technically the voltage divider, but now we have control over the reference voltage. Third one is directly connecting the reference voltage to a battery. And the fourth one, we are using a Zener diode. The problem with number 1 and 3 is that the voltage is fixed. You don't have any control over the reference voltage. Number 2, you have some control, but there is a problem with number 1, 2, and 3. Can someone think of what the problem is with number 1, 2, and 3? That is almost solved, I could say, in number 4.
Your input will be going against the VREF if it's alternating.
So the input voltage would not alternate that fast. And if you want to put it that way, all of them, they have the same thing, but that's another problem actually. But yeah, good point. But there's another problem with all of these, except number 4. What is an application of a Zener diode? What does a Zener diode do?
Voltage regulator.
Sorry, it's a voltage regulator. Perfect. Where do we use a Zener diode? Why do we use a Zener diode? So a Zener diode what it does, for those who had electronics with me, we had a lab, and in the lab, we explained about the Zener diode, and we had a lab that we would change the input voltages, and we will record the output voltage of, which was the voltage of the Zener diode. And we created a table which looked like this. I don't know if you remember, for those who had the class. So imagine this is V in, this is V out. And the input voltage went from, let's say, 5 volts to 6 volts to 7 volts to 8 to 9 and so on. But the output voltage would be 5.6, 5, oh, I'm sorry. Let's say we have a 3 volt. Imagine 3.2 volts, 3.3 volts, 3.4 volts, 3.4, 3.4. So the input voltage would range between 5 and 50 volts, but the output voltage would always be around 3.2 if we had a 3.2 volt Zener diode. And we have the same thing here. Most of the time, these op amps are used with a battery. And the example would be the dusk to dawn, like the solar, have you seen these solar lights they put around the houses, especially in Christmas, you will see a lot of those. And those have a battery. And the problem with that is that the battery, which is essentially the VCC, the supply voltage for this battery, the battery's voltage change. If you have a solar panel connected to it, it's going to fully charge during the day. And when that charges, what happens to this reference voltage if VCC increases? What happens to the reference voltage? The reference voltage also increases. And what happens when VCC drops? Reference voltage also drops. So if it's connected to the battery you're using at night, the battery is draining, and with it, you're reducing the reference voltage. During the day or when it's charging, the battery is charging, and the reference voltage is going up with it. So the battery itself, it's creating a variable situation, and it's changing the reference voltage. So number 1, 2, 3, because all of these reference voltage are actually related to the battery voltage. You can see number 3 actually is directly related to the battery. So what happens when the battery drops? It goes from 5 volts to say 3 volts. Then your reference voltage would drop from 5 to 3. And if you connect a sensor, let's say a proximity sensor or a photoresistor or an ultrasound, any type of sensor, obstacle detection sensor. Imagine you have an ultrasound sensor. First, it's giving you an alarm at 5 feet. When the voltage drops, now it's giving you an alarm at 3 feet. Sometimes it's going to be dangerous. So for example, if you have a proximity or an obstacle sensor on your garage, you don't want that obstacle sensor to change when your voltage is changing. And same thing for a dawn to dusk. Imagine that when the battery drops, now it's keeping the light on during the day or keeping it off during the night because the reference voltage has shifted. But in number 4, the reference voltage is actually related to VZ. So it's independent from the battery. Usually this VZ is a couple of volts lower than VCC. So imagine your VCC is like a 12 volts and your VZ is like 5 volts. If your voltage drops to 11, 10, 9, 8, 7, 6, even 5 volts, so the reference will be fixed at 5 volts. And usually it's much lower than the VCC. So you have a lot of space. And even if the voltage drops to half or something, this would work properly. Obviously, if the voltage, the battery is completely drained, the whole system would shut down. But you're going to have a lot more, it's going to be much more flexible, and the reference voltage would be fixed at a certain voltage for a variety of input voltages. Is this clear or yes? So number 1 and 3, almost the same. You don't have any control over the reference voltage. Number 2, you have control over the reference voltage, but all 3 have problem. The problem is that with changing the source voltage would affect the reference voltage, and we don't want that to happen. That's an uncontrolled situation. We have two types of competitors. We have a positive and a negative voltage competitor. The only difference between a positive and a negative voltage competitor is a positive voltage competitor input voltage is connected to the positive input here, or what we call it the non-inverting competitor. And for an inverting or a negative competitor, the input voltage is connected to the inverting input or the negative input of the op amp. That's the only difference that we have between the positive and the negative. For different applications, we can use different ones, but the function is basically the same. The only difference is in the voltage. For a positive competitor, the output voltage would be positive VCC. For a negative, it's going to be negative VCC. So not a lot of difference between it. It's just the difference on the V out, which could be high or low. This is an example of a positive or a non-inverting competitor circuit. As you see here, this is our input voltage Vn. As long as Vn is less than we reference, which here it's VCC over 2. Why is it VCC over 2? Because as we know, this is a voltage divider, and V reference would be R over R plus R, because these two R's are the same, times Vn or VCC, which here could be VC. Yeah, I'm sorry, VCC, yes, it's VCC. So V reference here would be VCC over 2, because the R's are the same. As long as this Vn is less than VCC over 2, the output V out, because V positive is less than V negative, then V out would be equal to negative VCC. And what is our negative VCC here? Or the negative supply rail voltage? It's ground, yes. So the output would be ground. And when V positive is greater than V negative, then V out would be equal to positive VCC. So at this point, V positive is greater than V negative, therefore V out would be positive VCC. You can see it shifts to positive. And again, when it's less, it's going to be less than that. So let's solve a quick practice problem. So for the following circuit, VCC is equal to 9 volts. R1, and this is R1 and this is R2, is equal to 2.5. R2 is equal to 65. What is V reference equal to? And if Vn is equal to 3 volts, what is V out? Gonna be equal to. I'll give you a few minutes to think. So what do you get for V reference? V reference would be equal to 65 over 65 plus 2.5 times 9 volts. What did you get? 8.67 volts. So V reference would be 8.67 volts. Now, if Vn is 3 volts, then Vn would be less than V reference. Then what would V out be? It's going to be 0 volts. Because this is less than the 3 volts. Then V out, I'm sorry. Vn is less than V reference. Then V out would be equal to negative VCC, which here it's the ground. 0. So we also have a negative voltage comparator. Only difference between the negative and the positive is that in the negative, the input is connected to the inverting or the negative input of the op-amp. And here, it's the shape of the signal is going to be the opposite. As long as Vn is less than VCC over 2, then V out would be equal to positive VCC. And at this point, when Vn is greater than VCC over 2, which is our reference, then V out would be equal to negative VCC. So let's see the breaking point. It's the exact opposite of what we had previously. We have a different type of comparator as well, which is called a window comparator. The window comparator is actually the combination of 2 different comparators, the inverting and the non-inverting comparator. If we combine 2 comparators, the positive and the negative, and we connect the positive of one op-amp to the negative of the other, and connect that to Vn, we create what we call a window comparator. So the window comparator has 2 reference voltages. One is the upper reference voltage, and the other one is the lower reference voltage. So if I want to find the upper reference voltage, this reference voltage here, I want to find this voltage. So what we do is we have to combine these 2. So we reference for the upper would be equal to these 2 resistors, R plus R, over all these 3. So it's going to be over R plus R plus R times VCC, which is going to be equal to 2/3 of VCC. And for the lower reference voltage, V reference for, I'm going to call it L, or the lower, it's going to be this over all these 3. So it's going to be R over R plus R plus R, which is going to be 1/3 of the R. So this would be 1/3 of VCC. Now, we can change these by simply changing these resistors, replacing them with the potentiometer. And the way that this works is, again, as mentioned, it's a combination of the inverting and non-inverting comparator. And initially, when the Vn is less than the lower V reference, the output would be equal to negative VCC. When Vn is between the lower and the upper, it's going to be equal to positive VCC. When it's greater than the upper, it's going to be, again, the negative. So in this area, it's going to be negative, positive, negative, negative, and going to have positive and again negative. And you're going to have a window in between that. So this is a very good has a lot of application. One application is creating PWM signals and a lot of applications in digital circuit design. So the initial switching condition of the circuit is the open collector output of the op amp A1 or off with the open collector output of op amp A2 on, sinking current. So V out would be equal to 0. So when one of them is off, the other one is on, and the output would be the output of the op amp, which is turned on in this situation. Let's solve a practice problem. For this, I think it's better to solve a practice problem, so you would better understand the concept. So for this particular example, imagine this R is equal to 4, this R is equal to 5, and this R is equal to 6. We want to find the V reference, the lower V reference, and the upper V reference. And we want to also draw V out. So we want to find the lower V reference and the upper V reference. Oh, and by the way, VCC is equal to 12.
Or is that the same VCC?
Yes, VCC is connected to both of them, yes. So the reference voltage, the lower reference voltage would be 6 over 4 plus 5 plus 6. times VCC, which is 12. So it's gonna be 6/15 times 12. What it's gonna be? 8.8, yes. Are you sure it's point?
That's the.
No, I don't think.
8.8 volts,
Double check.
or 4.8 for the lower.
It's 4.8. And what about the upper voltage? It's gonna be 5 plus 6 over 4 plus 5 plus 6 times 12. Which is gonna be. It's gonna be 8.8. Am I correct? So the upper voltage is gonna be 8.8, the lower voltage is gonna be 4.8. And the way that it works, if this is the input, the lower would be here, 4.8, and the upper would be 8.8. And the output is gonna look like this. It's gonna be 0, it's gonna be 1, up to here, again, here it's gonna be 0, to here, and then again from here to here, you're gonna have. So the green one is the input voltage, the blue one is the output voltage. Is it clear, or do you want me to solve another problem? Okay. Now, one application that we use for comparator voltage is for using it for a voltage level detector. One application that one of the devices that you may have seen is these voltage indicators for these AA or AAA batteries that you can build it using these op amps or any type of voltage detector, voltage level detector on these rechargeable batteries. Like if you have a I don't know, one of these power drills or something like that. You have like these rechargeable batteries that have these lights on them, these indicators, and you can build it using op amp. This is actually a good option if you want to do your final project. This is a very good, I could say this is a very good subject for your final project. So in this particular case, you would have 4 op amps, and you're gonna have 4 reference voltages. And depending on how much voltage you have in the output, and depending on the reference voltage, you're gonna have different lights turned on. So for example, if the voltage, imagine that this VR1 is, let's say, 5 volts. Then V reference 1 would be 4, V reference 2 would be 3, and this would be 2, and this would be 1. So when V reference or VR1 is 5 volts, then it's greater than V reference 1, greater than V reference 2, and greater than V reference 3 and V reference 4. Therefore, A1, A2, A3, and A4, all of them, V output would be equal to positive VCC. Therefore, all of them would be turned on, and you have all the LEDs turned on. Okay. But what happens when the voltage drops to, let's say, 2.5 volts? When it's 2.5 volts, then VR1, I'm going to call it V reference, or this voltage, is less than V reference 1, and less than V reference 2, but it's still greater than V reference 3, and it's still greater than V reference 4. So what happens is these two would be turned off and these two would be turned on. And it's going to show that the voltage is above 2 volts, for example. Let's solve a quick practice problem. I think we have a lot of time. Imagine if this is, all of these R's are 2 ohms, 2 ohms, 2 ohms, 2 ohms, 2, and 2. And VR1 is equal to, this is 12 volts. And let's say this is 4 volts. This voltage. By the way, this is a voltage divided potentiometer. You have 12 volts. It would be divided by this potentiometer, and you're going to have like 4 volts here. Which of these LEDs would be turned on? LED 1, 2, 3, 4, or all of them? Which one would be turned on? So here, all the R's are 2 ohms. VR1 is 4 volts, the voltage we got from a battery. Which LEDs would be turned on?
The first 3.
Sure. So let's find V reference 1. What is V reference 1 equal to? It's going to be 1, 2, 3, 4. So 4 R's, or R plus R plus R plus R, over 5R times VCC. What is V reference number 2? It's 1, 2, 3. We are left with 3. So it's going to be 3R over 1, 2, 3, 4, 5 over 5R times VCC. V reference 3 is equal to 2R over 5R, or 2/5 of the R times VCC. And V reference 4 is equal to 1/5 of VCC.
Just the first.
Yeah. So what is V reference 4? What is 1/5 of 12? 2.4. Thank you. What is 2/5 of 4.8? What is 3/5?
7.2.
7.2. And what is 4/5? 9.6. So 4.4 is greater than V reference 4, but it's less than V reference 3. So only LED 4 would be turned on. One of the LEDs would be turned on. The rest of it would be turned on. Okay, that's it. Again, your exam, I think I've posted a announcement for the exam, didn't I? So your exam is going to be next weekend. It's going to start, it's going to be online. We're going to have a review session before that. And your deadline for your final project is going to be December 3rd. And I've already posted the instructions on how to prepare your report for your final project and what is required in the final project. Okay, thank you so much, and you have a great Thanksgiving. Great.